Okay, so our next speaker is Hany Abdulsamad, who will present State-Regularized policy search for linearized dynamic systems.
Okay, thanks. So I'm going to be talking about something a bit different from most of the other talks. What I'm interested in, I come from a background in robotics. What I'm interested in is model-based reinforcement learning. And in contrast to, let's say, the discussion yesterday in the panel, there is this field that's called model-based reinforcement learning, but I want you, when I say model, I want you to think of something that's approximated, something that's learned from data. So we never actually have a full model of, let's say, a complete task. So these models are learned on the fly, and we use them to facilitate the reinforcement learning problem. So let me just very quickly motivate this. Why use model-based policy search and not go for the free model-free version? Well, I mean, this is a very old discussion in the community, I guess, and very briefly, basically people argue that model-based approaches can be very often more sample efficient because you're trying to not directly work with the samples, but try to understand the underlying model and exploit that, and that may help you also with the generalization capability of your controller, and you maybe even be able to reuse the model if that fits another task. But there are also some possible pitfalls, and of course, if you approximate bad models, you're stuck with them. And the second thing is basically also related. If you overtrust the validity of your model, you also sacrifice, let's say, you'll have a worse performance overall. And there's also poor scalability. So people ask the question, to which point is it more efficient to learn a model and then learn a policy from that when you have, let's say, a robot with 50 degrees of freedom or whatever. It might actually be more efficient to directly learn the policy. So I'm going to be discussing basically the first two pitfalls, bad approximations and overtrusting the model, and how to, so we have an intuition of how to have a better algorithm that deals with these problems. So let me define the general problem. We're looking at a fully continuous finite horizon MDP, and I mean fully continuous because it's continuous in state and action. This is the problem in robotics that we want to solve. So you have a state space S, an action space A, and a time horizon T. You have usually a stochastic transition dynamics, and you have some cost function depending on your task. We define a distribution, a policy distribution pi, and a state distribution mu. So the overall task is to minimize the total expected cost, and as you see here, we have those integrals over the continuous state action space, and generally solving this problem is very hard. There are only for rare cases there are closed form solutions, and in our field doing discretization is not an option most of the time. So if we want to solve this, we would like to have it in a continuous form. So people have devised the scheme, which I'm going to call, it has a lot of names, I'm going to call iterative stochastic optimal control. This goes back to the 70s or 60s, and this has been devised by Jacobson and Main. Basically, I think they were the first to introduce something like this. So the main idea is you start with an initial state distribution and initial policy. You apply this policy on your system to draw samples. You collect these trajectories. You learn local models of your dynamics and costs around these trajectories, and try to minimize the cost in this region of the state action space, and then go for a policy update and basically iterate in this cycle and hope, basically, there's nothing more than hope to converge to something that's optimal. So basically, there are a lot of algorithms that use this structure. I'm going to mention differential dynamic programming, iterative LQG, and maximum entropy LQG, which has been very successful in recent years. I'm going to also be working with this framework. But there is something very important about this approach. It's dependency on those local learned models, and you have to be very careful that these models are only valid in a very small region of the state action space, basically where you sample your system. So overexploiting them in one policy update is dangerous. You might actually diverge between two iterations. So it's very crucial to stay close to this region where you have sampled your data, to stay close to your models. And for that, people have devised different regularizations of how to do this. So regularization of your policy update. Most algorithms, I'm going to say like DDP or ILQG variants, they do this regularization in the policy space. So what they basically do is they say, I'm going to scale down my controller and I'm going to, let's say, apply only 10% or 20% of this step that I've taken. And what the intuition is, there's this underlying assumption that if you apply only small changes in the control, you'll also have small changes in the state distribution. But this is, in my opinion, this is a very restrictive view, because if you have highly non-dynamical systems with very complicated cost functions, small changes in the state could actually mean very high changes in dynamics or in the cost. So this is basically the motivation. Like I said, regularization is key. The dynamics and the cost function that you are learning are functions of the state and action. And in my opinion, regularization has to happen in both spaces, or in the state action space, basically. And what we hope to be able to achieve is to have more effective policy updates, which would also lead to less needed samples, which is very crucial if you're working with a robot, let's say. So basically, we devised this new approach. This looks a bit intimidating, but please bear with me. So the first line is the main objective, right? Main optimization objective, and it's subject to the first constraint is just a stationarity constraint. It tells you that if I apply a state distribution propagated through my policy and my transition dynamics, I'll get a second distribution. And there are some normalization constraints, and the red constraint that you see, this is basically this is a relative entropy constraint. This is called Bach-Leibler divergence, which is a divergence between the next policy I'm going to optimize and the policy from the last iteration. And what this does is it does the regularization in the policy space. And it can be shown that under certain conditions that this is equivalent to iterative LQG. So what we've done is we went and said, okay, let's use the same trick. Basically, this KL divergence is inspired by relative entropy policy search. And we said, okay, we can also apply another constraint on the state distribution, right? So Q of S is basically the last state distribution from the last iteration of your reinforcement learning algorithm, and mu will be the next one. And what you're saying is, I want to bound the change between mu and Q by some step eta. And it turns out this is, of course, let me say this is, in the general case, this is a highly non-convex problem. So what you're hoping to find is some locally optimal solution only. It depends on your initialization of the policy and some other parameters. But if you solve the primal problem, you will see that your optimal policy is some softmax distribution that weights your optimal Q function, and your Q function will show you what these new constraints have added to the classical, let's say, formulation of the Q function. So the red term is basically a cost in the action space, while the new constraint is a cost in the state space. And of course, you have your expected cost over the value function v for the next time step. Now, if you go for the dual problem, you can show that you can find the optimal value function as a log of I'm not going to go into details about what this really means, but it's basically this formulation, and it's an optimality condition on the v function, and the second optimality condition is on mu, and basically this is just a forward pass for mu and a backward pass for v. Now, it turns out if you learn models that are linear Gaussians in the dynamics and quadratic cost functions, you'll have very beautiful math, and you can solve this in closed form solution in a closed form fashion. So let me now just give you an outline of how the whole thing works. Just let me go very quickly over. Oh, I'm sorry. So there is this problem, of course, that like you see in the Q function and basically also in the V function, you have the problem that your value function depends on the state distribution mu. And your policy depends on the value function. And your mu depends also on the policy. So you have this circular dependency. I want to find an optimal value function that has some certain condition on the mu function. So this introduces the circular dependency, and it's kind of it's not easy to solve in this sense, but we have devised a way of doing this. The algorithm is basically follows the stochastic optimal control scheme. So you have an initial state distribution, you have a policy Q, you choose your hyperparameters. Basically, these are the bounds that you choose, and you sample trajectories with the initial policy, learn the local dynamics and cost functions, and then to reach this optimal V function, you can use those optimality conditions that I just showed you in an iterative way. So you descend basically on the value function, then you descend on the mu function, and we can show that it converges, and it's actually much more faster than descending on the actual gradient of both, right? Using the optimality condition is a bit different. And what you do then is you update your other dual parameters also until converges, and basically this is one loop of the algorithm. You just go through until you converge. So I'm just going to go. We have a few experimental validations. It's very simple. We compare to maximum entropy ILQG, which does the regularization in the policy space, and we have these two tasks. So we have a double link and a quad link, and what we want to test is basically so we define a quadratic cost for the swing up of both and a non-quadratic cost, and we compare to maximum entropy ILQG. And very quickly you'll see that we are able to sometimes we reach the same final cost as other policies, but most of the time we are much more sample efficient, and most of the time it's 30 to 50% more sample efficiency, which is a huge thing in, let's say, I mean, I know this is a constructed example and a simulated result, but if we can show this on a real robotic system, this could actually be a huge advantage. The same thing you can see also for the quad link. The quad link is, of course, much more dynamical, and you can even show that you can reach a better final cost in a limited number of iterations. So basically, this is it. I want to introduce something else that we've worked on, which is another bound on the what I call the action differential entropy bound. So the problem is those relative entropy constraints that I just introduced, they work on the mean and variance of the distribution, be it an action distribution or a state distribution. And what could happen is that your optimizer could actually shrink the variance of one of those distributions in such a way that it meets the constraint, but without actually moving in the direction of the mean of this distribution. And this is a problem in this sense, because you can imagine that you can start with a huge variance on the control, and it would just shrink into 0 and say, okay, I have better costs here. Let's just stay with 0 control and 0 variance. So what we do is we explicitly set a lower bound on the change of the entropy between iterations. And this is inspired by work in the stochastic search domain. What this does is basically it preserves the policy variance and from prematurely collapsing, and basically lets you control how the algorithm searches in the action space. So without going into details too much, this is the same problem, just in a compact way. What you see, the red constraint is this new constraint. So I'm bounding the change of the entropy of my new policy in comparison to the old policy by some bound delta. And what you see is this doesn't change much actually in the overall formulation. You will get a policy with a new weighting. It's still a softmax policy. Your value function and your state distribution still have this circular dependency. We didn't change much there. What changes is you have to optimize over a new variable, and you of course have to tune maybe this delta, which is kind of annoying. Let me now jump quickly to the conclusion. So the main idea is learning these models on the fly may actually be helpful for reinforcement learning, but it's very important to listen to what your model is telling you. If your model is local in a region, don't try to exploit it. And we have shown that this may actually give you a better results at the long run. We have shown that our approach is much more sample efficient, at least in simulated environments, and we hope to be able to demonstrate that on a real robot in comparison to other state-of-the-art methods. And although this is somehow a limited approach, we hope to be able to leverage learning those local controls and local models in such a way that we can learn a hierarchy of other representations. So let's say learn a neural net that generalizes. This is something that has been done, but we want to show that maybe we're even more efficient in learning such representation. So you can learn maybe a neural net that generalizes over multiple linear controllers and may even generalize to different tasks. So that's it. Thank you.
So I'm just trying to disentangle your method from a lot of others. So there's are you familiar with trust region policy?
Mm-hmm.
So all of those natural gradient.
Yes. Yeah.
So I'm gonna try to. I'll say how I understand what you're doing. You can tell me if it's wrong. So trust region policy optimization will sample trajectories like you do, and then they'll define a type of trust region in more of a empirical sample way. I mean, you could say that's sort of an empirical model in some sense. And you're kind of compressing those into a model of your choosing, and then you're defining the trust region in terms of that. Are you also defining sort of the gradient direction using that model? So is that an accurate understanding?
Well, the thing is that we actually don't use the gradient. So the trust region trajectory optimization is a fully, I'm going to say, so it's based on a gradient approach. You update this neural net policy in a gradient fashion. And actually, to be honest, if you want to go to compare, you should also compare to relative entropy policy search, which was right. But here what we leverage is this model. We learn this model explicitly, and we try to we get this very nice closed form solution so that we don't have to apply the gradient, basically. This is the main change. Yes, yeah.
Have you been able to compare well, I guess, so you compared to relative entropy,
to model-free approaches, you mean? We didn't do that explicitly in this paper, but I think it's something that we should do. To be honest, it's always hard then to say, okay, which model-free algorithm do you compare to? And maybe this is actually a trust region trajectory optimization. Maybe it's a good one because it's one of state of the art. Yes, but it's still like always there's a discussion. Oh yeah, well this optimization problem works in this setting. It doesn't work in this setting. So it's kind of hard, but we should do this comparison. I agree. Yeah.
Thank you. We're running a bit out of time, so we have to switch.
Okay, no problem.
Thank you very much.
Thanks.